I'm Berrien, Dean of the College of Atmospheric and Geographic Sciences, Director of the National Weather Center, and Vice President for Weather and Climate Programs here at OU. We're talking about the carbon cycle. And one of the things that we've been challenged by is to actually quantify and differentiate in time and space where CO2 is coming from and where is it going to. Not just where is the fossil fuel burning taking place, but how much is going back into the forest of the world and where and under what conditions. How much is going into the oceans and where and under what conditions. As we talked about earlier, we know the broad numbers. Roughly 100 billion metric tons are being exchanged between the atmosphere and the terrestrial biosphere, and about the same amount between the atmosphere and the oceans. The devil is always in the details. Where? How does it vary year to year? Under what climatic conditions does it change? So in order to get at that problem, we approach it in two different ways. One is we develop mathematical models of the terrestrial biosphere, of the oceans, and shall we say from a kind of a bottom-up calculation, we try to estimate what the terrestrial system is doing and what the oceans are doing, how the atmosphere is interacting. But how do you check that? Use up all the information you have in order to build these models. And so in this case, we use a top-down approach. And the approach that we're currently employing as a planet is to use satellites to measure how much carbon dioxide there is in the different parts of the atmosphere at one time of the seasons versus another. And then to try to back out of those differences or use it as a check on these models. What's happening in the terrestrial and oceans? And as a planet, we were successful in 2009, led by the Japanese Space Agency, in their launch of GOSAT, Greenhouse Observing Satellite. But GOSAT was the first time that we put an instrument in space to measure carbon dioxide and methane, the two most important carbon greenhouse gases. Shortly thereafter, the United States launched the Orbiting Carbon Observatory, OCO, the molecular form of CO2. Unfortunately, that instrument headed for space didn't make it, and it ended up in the South Pacific Ocean because of a launch failure. In 2014, we were lucky in July to have a successful launch, this time of OCO2. We rebuilt the instrument and it is now on orbit. So right now, the planet has two instruments, Japanese instrument, US instrument, measuring the concentrations of CO2 and methane. For the US, we only measure CO2. And out of these very careful measurements of CO2, we try to back out what the sources and sinks, what is happening at the surface. Both of these satellites have a very narrow swath. The Japanese slightly larger, a little less accurate. The Orbiting Carbon Observatory is smaller, more accurate. But in each case, you're sampling a very big atmosphere. So you may remember there was a time in high school when you had too few of equations for too many unknowns, and you can't get the solution. We're kind of on the edge of that. But there are plans for the future. The Europeans, the French and the Germans, will be launching a very interesting mission, and that's an active mission. For GOSAT, the Japanese mission, for OCO, the US mission, we use reflected sunlight to determine those concentrations. So that means we can only make measurements where there's a lot of light. Can't see the high latitudes in the wintertime, can't see changes at nighttime. But for Merlin, the methane mission that the Germans and the French are going to fly, they're going to take their light with them. They're going to have a laser on board. One frequency will be on the absorption band of methane in the atmosphere, and the other frequency will be just off that. And so out of that, by comparison, we can make an active measurement of how much methane there is in the atmosphere. Satellites that I've just been mentioning, GOSAT and OCO and TANSAT and so forth, all are in what's called low Earth orbit. They orbit the Earth about 400 kilometers up, from North Pole to South Pole to North Pole to South Pole. And then as the Earth turns beneath it, you trace out thin lines from pole to pole. You're sampling the global Earth, but still just sampling a small amount of it. There's a mission that we're working on here at OU that would take a very similar instrument to the Orbiting Carbon Observatory, but put it on a geostationary platform that stays at a fixed point above the equator. A carbon measuring satellite. In this case, we would actually measure carbon, methane, and CO, carbon monoxide, and essentially map it wall to wall every kilometer. That would be a radically new, different way of approaching the problem. So what we're really looking at, and what we'll be talking about in this class, is a system of systems, once again, but in this case, a system of systems to measure the carbon cycle.